In the previous video, we used SPSS to select 4 different non-random samples from our population of 250,000 individuals. We had SPSS summarize the results for one of the variables, var B, in each of the samples and compared them to what we know is true of var B in the population. All 4 samples' results were not very accurate. The results were a little better when the samples were much larger, but they were worse when we accidentally selected the sample from a portion of the population that wasn't very representative. It was a little better when we accidentally selected a section of the population that seemed more representative, but we really didn't know where to look in the population for a representative group. Even when the sample included nearly half the population, the results weren't very accurate as an estimate. None of these samples was a random sample. I had SPSS pick the sample from the cases that seemed easiest to get to for me, most convenient to select, or from a part of the data file where I thought the individuals would be typical of the population. We relied on my judgment, and I frankly wasn't very good at it. Let's change our sampling method and see if random samples do any better. In random sampling, the researcher doesn't decide where in the population to pick people to be surveyed. Instead, each case in the population is given an equal chance of being selected, and a random process picks the individuals for the sample. So let's see how well a random sample does at trying to represent what is true of the population. I'll go to Data and change the selection method to a random sample of cases. Now here's where it gets fun and potentially risky. For all the other example samples we looked at from this data file, I knew what the results were going to be ahead of time because I've done them before and I knew which cases it was going to select. The first 100,000 cases were the same 100,000 cases each of the times I've ever asked SPSS to select them, so the results were always the same. However, when I now tell SPSS to generate a random sample, I don't know which cases it will select to include, so I don't really know how good the sample will be at representing the population. Every random sample I ask it to select is different than the previous random samples it has picked. However, in theory, 95% of all random samples of a particular size from even a very large population should produce results that are within only a few percentage points of the actual percentage distribution in the population. So we're going to test this. I'll tell SPSS to do something pretty daring. I'm not going to tell SPSS to pick a random sample of 100,000 cases. I'm not going to tell it to pick a random sample of 10,000 cases or even 1,000 cases. I'm going to tell SPSS to select a random sample of only 400 cases from the total population of 250,000. So I'm going to say exactly 400 from the first 250,000 cases. That's the whole data file. The mathematics of random sampling indicates that 95% of random samples of 400 from a very large population should produce results that are within plus or minus 5 percentage points of the true percentage. Now this is where this demonstration turns into a high wire act, like walking a tightrope without a net. It could go really badly. I could get a sample that is one of the 5% of all random samples that would be not so good. That means I have about a 1 in 20 chance of getting a bad sample and a 19 in 20 chance of getting a good sample. I'm going to bet I get a good sample, but I have no safety net if I fall off the tightrope. So let's see what I get. Now we've selected the sample. Let's look to see which cases SPSS picked to be the 400 cases and from which part of the data file. When we ask SPSS to select cases and filter the unselected cases out, it creates a variable called filter. On the far right of the data set, encodes the unselected cases 0, and it codes the selected cases as 1. Therefore, we can click on the top of this file and then ask SPSS to find the cases coded 1. So we'll click on Find Next, and it'll find the first case that was selected by our sampling process to be included in our sample. So here is our first case, and it's case number 355. It's pretty far down the list from the top. Let's look at our second case that was selected. It's case number 990, And the next case is case number 2059. The next case is 2599, and so on. As you can see, the random sampling process, as you can see, what the random sampling process did was to select cases that were scattered throughout the whole population in no apparent pattern. Let's generate the frequency distribution to see how well this sample's results compare to the other samples and to the population characteristic. So we'll go up to Analyze, ask for descriptive statistics, and the frequency distribution for var-B. Now this should completely amaze you. SPSS did in fact only analyze 400 cases in the sample, and yet there are two important things we notice about the results it produced. First, individuals who gave any of the 5 possible answers are in fact represented in the results, even the rarer or less common responses. And second, each of the percentages is within only a couple of percentage points of what we know is the true distribution in the population. Instead of 39.1, which we know is the true percent that said never refused, this sample said 40.3. Whereas in the real population, 48.3% said they had refused only once. In our sample, it's 48.8%. Instead of 9%, as in the total population, our sample said it was 8.5% that said 2 or 3 times they had refused. Instead of 3.1%, in population it said they had refused 4 or 5 times, the sample said it was 2.3% that did it. And the last category, the population indicated that 0.4% had refused 6 or more times. And in our sample, it's 0.3%. This is amazingly close to what is true of the population characteristic. And this was with a sample of only 400. Notice that even though a random sample of 400 should have a margin of error, margin of sampling error of plus or minus 5 percentage points, this sample is much closer to the real distribution than that would suggest. And that's true of most samples. The plus or minus 5% is the outside limit of how close it's likely to be. Most of the samples would actually be closer to what is really true. In our case, they're off by less than 1% for each of the categories. So I think this is pretty amazing. But let's do another random sample and see what we get on that. So I'm going up to Data. I'm going to say Select Cases. So I want to turn off the selection that we've already made. So I'm going to say Pick All Cases and click OK. So now it has released all these other cases. I'm going to delete this filtered variable and let it form a whole new filter for us. We'll go back to Data, Select Cases. We'll tell it we want a random sample of 400 from the first 250,000 cases. And we'll say OK. And now it's made a whole new selection. And if we wanted, we can double check here and ask it to find the first one. And this time, the first case that it found that had been selected was 872, which is a much different case than was the first selected one in our first random sample. So we know this is a different set of respondents in this sample. So we'll close this up and we'll go ahead and ask for another frequency distribution on var-B, say OK. So here's the second random sample. And this one's a little bit different than the first one we drew. So instead of 40.3%, we're estimated as having said never. This time it finds 41.3%. 48.3% refused only once, 7% 2 to 3 times, 3% 4 to 5 times, 0.5%, 6 or more times. So these are all a little bit different than what we found in the first random sample. And in fact, in most cases, they're a little bit farther away from what we know to be true than what the first random sample suggested. But these are all still only 2 percentage points or less from the actual percentages in the whole population. So this is still a really accurate, close approximation or estimate of what is true of the population, again, based only on a random sample of 400. And that's pretty amazing. So let's do one more time, just to see how well our luck holds up here. I'm going to turn off the selection, clear out the filter. Oops, clear. Now we'll go back and select a new sample. So now it's selected a new sample. We'll go back up to Analyze. We'll ask for the descriptive statistics for var B, and we'll get it done. Here's the new set of output for the third random sample from this population. And notice that it's a different distribution than we got the last time. It's different from what we saw in the first one, but it's still very, very close to what we know is really true in this population. So we've seen 3 separate different random samples from this population, all of which produced results that are amazingly close to the true characteristic in the population, are far better and less biased than what any of the other samples we looked at produced, even though some of them were 250 times larger. So this should convince you that relatively small samples actually can, if they're random samples anyway, actually can accurately represent, within the margin of sampling error, what is true of a much, much larger population. However, there is an important question that remains. Almost never do all individuals selected in the sample we use for surveys end up responding. We may start off with a random sample that, if everybody responded, would produce these very accurate estimators of what's true of the population. But it's virtually never the case that 100% of the people selected in a sample actually respond. So the next question we want to address is, can a random sample be accurate if not everyone responds? In the next video, we're going to explore this question. It is important to our confidence in the usefulness of sample surveys.